This slide doesn't contain enough information. That's why we're moving to the next slide. Let's take a closer look at the process for microbial production of SCO, starting with submerged fermentation. In this method, microorganisms are grown in a liquid medium, which allows for efficient control and monitoring of the growth conditions. The amount of lipid they produce mainly depends on factors like the mode of cultivation, the carbon and nitrogen sources used, as well as the pH and temperature of the environment. When it comes to the carbon source, glucose is frequently used because it's a simple, readily available carbohydrate. It can be in the form of monosaccharides, disaccharides, or even complex forms like CMC, which is carboxymethyl cellulose. To trigger significant lipid accumulation, you need to increase the amount of these carbohydrate sources accordingly. Now, moving on to solid-state fermentation, this method involves growing microorganisms on a moist, solid substrate without free-flowing liquid. Here, the carbon sources are often agro-industrial products or residues, such as wheat straw, cereal-based products like bran, or other agricultural wastes like orange peel, pear pumice, press cake, and brewer's spent grain. Because these substrates vary in composition, sometimes a pretreatment, either chemical or enzymatic, is necessary to break down insoluble materials into monomers that the microbes can readily utilize. For example, Aspergillus oryzae can directly convert cellulose-rich materials like wheat straw into SCO, thanks to its enzymatic capabilities. Overall, both methods leverage different substrates and cultivation conditions to optimize lipid production, which is key to developing sustainable, microbial-based sources of valuable lipids. Let's start with the low-cost materials we can use for microbial lipid production. These include glycerol, which is a byproduct of biodiesel production, commercial sugars, plant materials, and lignocellulosic biomass. All of these are affordable and readily available, making them ideal for large-scale processes. Moving on to nitrogen sources, we see that both organic and inorganic options are used, either alone or in combination. Examples include yeast extract, urea, peptone, glycine, potassium nitrate, ammonium sulfate, and ammonium nitrate. Notably, yeast extract has been shown to increase lipid accumulation significantly, with a value around 64.2%. The CN ratio, or carbon to nitrogen ratio, also plays a crucial role here. It influences lipid buildup considerably, with ratios ranging from 35 to 340 mol. Adjusting this ratio can optimize lipid production depending on the microorganism used. Speaking of microorganisms, we have several fungi of interest. Cunninghamella echinolata and Mordirella isabellina are two notable examples. Both can grow on glucose and fructose, but it's interesting to note that M. isabellina doesn't grow on sucrose, which highlights some metabolic preferences. Other fungi like Aspergillus oryzae, Cunninghamella elegans, Cunninghamella echinolata, and Mordirella isabellina are also used in these processes. Understanding their growth patterns and nutrient requirements helps us tailor the fermentation conditions for maximum lipid yield. All these points tie back into our overall goal: finding cost-effective, sustainable ways to produce microbial lipids for various applications. By selecting the right materials, nitrogen sources, and microorganisms, we can optimize the process efficiently. Let's talk about the value of mushrooms, how they are cultivated, and the preservation methods involved. According to data from Matilla and colleagues, different mushroom varieties like Agaricus bisporus, Pleurotus ostritus, and Lentinula edodes have notable protein contents, ranging from about 1.6 to 2.1 grams per 100 grams. What's interesting is that mushroom proteins are relatively rich in amino acids, especially glutamic acid, which can make up anywhere from 12.6 to 24% of the amino acids, and aspartic acid, ranging from about 9.1 to 12.1%. Arginine is also prominent, making up roughly 8.7 to 13.9%. Another key point is that these proteins contain important sulfur-containing amino acids like methionine and cysteine, which are crucial for various metabolic processes. Moving on, Moisture content in mushrooms is quite high, typically between 85 and 95% of their fresh weight. This moisture level is influenced by several factors such as the timing of harvesting, watering conditions, temperature, and humidity during cultivation. Understanding these aspects helps us appreciate the nutritional value of mushrooms and the importance of proper cultivation and preservation methods to maintain their quality and health benefits. Let's start by looking at the carbohydrate content in mushrooms. It can range quite a bit, from about 35% up to 70%, including both digestible and non-digestible carbohydrates. And this variation actually depends on the species we're talking about. Now, focusing on the cultivated mushroom, which is what most of us are familiar with, it has a fascinating nutritional profile. For instance, about 75% of its fats are unsaturated fatty acids, which are the healthier types of fats. Moving on to vitamins, mushrooms are a good source of several B vitamins, including thiamine, riboflavin, niacin, biotin, pantothenic acid, folic acid, and even vitamin B12. This makes them quite valuable for maintaining energy metabolism and overall vitamin intake. They're also a good source of dietary fiber. Specifically, they contain water-insoluble fiber in the form of chitin, which is a polymer made of N-acetylglucosamine. Additionally, they contain non-starch polysaccharides like beta-glucans, which are known for their health benefits. In terms of fat content, it's quite low, less than 10% of dry weight, making mushrooms a low-fat food. Examples of species with this profile include Lentinula edodes, the shiitake, and Pleuratus ostreatus, the oyster mushroom. Let's not forget minerals. Mushrooms provide macroelements such as calcium, magnesium, sodium, phosphorus, and potassium. They also supply microelements like copper, iron, manganese, and zinc, which are essential for various bodily functions. However, it's important to be aware that some mushroom species can accumulate harmful elements, including radioisotopes. This is a consideration, especially in terms of environmental contamination, as some species can absorb detrimental substances from their surroundings. So, to sum up, mushrooms are a nutritious, low-fat source of vitamins, minerals, and dietary fiber. But we also need to be mindful of their potential to accumulate harmful substances depending on where they grow. This highlights the importance of proper cultivation and environmental awareness in mushroom consumption. Let's take a closer look at some of the key bioactive compounds found in different mushroom species and their health benefits. L. edodes, or shiitake mushrooms, are known for their anti-tumor, anti-hypertensive, and hypocholesterolemic activities, as well as their antibacterial properties. These effects make them valuable not only as a nutritious food, but also for their therapeutic potential. G. lucidum, commonly called ricey, exhibits antimicrobial and anti-HIV effects. It contains important compounds like beta-glucan polysaccharides and ganoderic acid, which contribute to its powerful antitumorigenic effects. These compounds help modulate the immune response and fight off various diseases. Pleuratus species, or oyster mushrooms, are celebrated for their hypocholesterolemic, anti-inflammatory, and immunostimulatory activities. They support heart health and boost the immune system, making them a beneficial addition to a healthy diet. Now, moving on to cultivation, it begins with the development of spawn, which is essentially the mushroom seed. Next, we prepare the substrate, the material on which the mushrooms will grow. Once the spawn is introduced into the substrate, we allow it to run or colonize fully. Following that, we observe mushroom development, which involves the formation and growth of the fruiting bodies. Understanding these stages is crucial because they directly influence the quality and yield of the mushrooms. Throughout this process, harnessing these bioactive compounds can enhance health benefits, including immunomodulation, antioxidant activity, cardiovascular support, and even detoxification and hepatoprotection. In essence, proper cultivation not only ensures a good harvest, but also maximizes the medicinal and nutritional potential of these remarkable fungi. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's explore the processing of preservation, focusing on both short-term and long-term methods. When it comes to short-term preservation, cooling is key. Refrigeration at around 22 degrees C typically lasts 1 to 3 days, while at a slightly cooler temperature of 15 degrees C, it can extend to 2 to 3 days as well. For minimal processing, controlling microorganisms and preventing decay often involves chemical treatments. These chemicals help inhibit disease-causing agents and slow down spoilage. There are several pre-cooling methods used to prepare food for storage. These include air cooling, forced cooling, ice bank cooling, vacuum cooling, hydro cooling, and evaporative cooling. Each method is chosen based on the type of produce and the desired preservation outcome. Chemical compounds also play a vital role in preservation. Substances like oxine, which is stabilized carbon dioxide, hydrogen peroxide, arsenic or EDTA combined with citric acid, and other agents like sodium erythorbate, calcium chloride, ascorbic acid, sodium metabisulfite, and jasmonic acid with methyl jasmonate and ethyl alcohol are commonly used to prevent oxidation, microbial growth, and decay. Moving on to long-term preservation, freezing is a popular method, typically at temperatures from -25 to -30 degrees Celsius. This effectively halts microbial activity and enzyme actions, preserving food for extended periods. Canning is another method, allowing foods to be stored for up to 2 years. This involves sealing food in airtight containers and heat processing to destroy pathogens and spoilage organisms. Drying methods include hot air drying, vacuum drying, freeze drying, fluidized bed freezing, and microwave drying, including microwave vacuum drying. These techniques remove moisture, which is essential for inhibiting microbial growth and extending shelf life. Overall, these preservation methods, whether short-term or long-term, are all about controlling environmental factors like temperature, moisture, and microbial activity to keep our food safe and fresh for as long as possible. Thank you so much for your time and attention.